of today's lecture has to do, ladies and gentlemen, with the general topic we talked about last time. When good programs go bad, when bad things happen in a program, what do you do? Talked about the inconvenient fact that we often think about solving the problem. How we're going to go about achieving the functionality that's wanted within a program. How we go about giving the user the ability to solve their problem using our program. And that motivates us. I mean, a lot of people just love, helping to contribute to solving people's problems. I know that I do. And then as food for a lot of thinking. We create algorithms. We design data structures. We architect large systems to deliver value by solving problems. But the awkward fact is, the inconvenient fact that sometimes we don't have the opportunity to solve the problem as posed because something goes wrong. A network resource is not available. A disk is full. The user enters something that we can't understand. There's data corruption in a database. All these are awkward facts of existence. And when we build a program, we need it to be able to handle these situations gracefully at some level. And secondly, if our program has problems in it, if there's inconsistencies in it, oversights, maybe because of mistakes we've made, maybe because of mistakes someone else has made in working with our code, we want to know about it as soon as possible. Okay? So we're going to be talking today about the later part of what I've just described. To wit, the use of techniques for aggressively going up there and finding problems with our programs. Okay? And these techniques are going to be applied for you more or less immediately on assignment 2. Okay? So, talked about bad problems, and we talked last time about 2 of these in order. Return codes and exceptions. Okay? So, who can remind me? I don't think I'll privilege the person. What are exceptions used for? What are the situations where we might use an exception? Good. The things that don't happen very often, but we have no ability to sort of control. We have no ability to control how much memory someone has, available to them on their machine. Maybe there's some god-awful big program sucking up their memory. Bloatware that's sucking their memory back. So that would be a case where an exception might be needed, because we can't just pass back any old value, and we really want to be able to enforce handling. We want to be able to say, look, this is not something to take it lightly. You got to handle this possibility. So that might be a case where we want to have an exception in place. How about other things? Yeah, failed connection. Something, we can't do our work. We can't do our work if we can have the memory. We can't do our work with a failed connection, right? And we say, okay, somebody's got to handle this. And that was the big draw of exceptions in many ways. The language enforces it. That sounds weird. I try to step out of my sort of conceptualization of this. And the language, when I say the language forces you to handle it, what do I mean in concrete terms? What will happen if you don't handle a required exception? Okay. This is true for certain types of exceptions, what are called runtime exceptions, where that's like left till runtime. There's another type of exceptions. In fact, the dominant one in Java, that if you don't handle it, something else happens. And what is it? It won't compile. You actually can't compile your program and say, you got to handle this. Either you got to handle this, or you got to tell others that you're not handling this so that they have to handle it. Either the buck stops here where you are and you got to deal with it, or you tell someone else, look, the buck's going to stop with you. Okay? You're going to handle it. These are sort of basic aspects of contracts. For example, if you put out a contract for someone to do renovations in your home, it needs to be clear in the contract who's going to handle cost overrun. So maybe it costs more than expected. Maybe it takes longer than expected for them to do the work. Maybe they open up the area behind your cabinets and they find that it's got all sorts of structural problems. So maybe there's ants all over it or something. Or maybe there's asbestos and it has to be cleaned out in a way that minimizes the health risks or something like that. All those are possibilities. And the question is, who handles that? Okay? In the contract, you say, hey, contractor, you got to handle it. It's your job as part of the contract. Or the contract would say, you, as the user of this contract, as the sort of person in the contract that's got to handle it. That's got to be clear, right? Because otherwise it just leads to misunderstanding and, they find the asbestos and then there's a fight between them. You handle it. No, you handle it. So in our legal system, we have mechanisms in place. This is what lawyers spend a lot of time doing, is like, who's going to handle this? Now, a contractor, of course, if they've got to handle it, they'll charge more. If we got to handle it, we want to be charged less by the contract, because we're shouldering the risk. And it's like that, ladies and gentlemen, with code. Okay? So if foo is going to call bar, either it's got to know, okay, bar is going to clean up after itself if it can't get a network connection, or if it can't allocate the memory, which is fine. That's bar's responsibility, or that's foo's responsibility as the caller of bar to deal with that situation. But it's got to be clear. And that's what exceptions are about. That's why in Java, when you declare foo as a function, you'll say foo, maybe it returns an int, okay? And then maybe it takes some parameters, some things that get passed to it, and then we say throws some exception. Maybe you can throw E1 and E2. These are different types of exceptions. Maybe you could throw out-of-memory exception, and maybe you could throw file-not-found exception. In which case, this is saying that, let me call it bar, because before I said if foo calls bar. If foo calls bar, now foo's got to handle these things. Because bar's saying, hey, that's your responsibility, it's not my responsibility. On the other hand, bar can handle it, in which case it doesn't have to say throw it, and foo can call it with confidence that bar's going to clean up after itself. It's going to kind of do that thing. So exceptions allow us to enforce that someone else has got to handle it. We can say basically, hey, you got to handle it. It's just part of the contract. You want to call a different function, that's fine. So if you want to get a different contractor, that's fine. But if you're going to deal with me, you're the one. If you're going to deal with me as a contractor, you're the one who has to handle asbestos costs. So small contract. Okay, so exceptions here. They have a language mechanism. Your program won't compile, folks, unless it cleans up properly after itself, unless it properly handles this. Now, it turns out I'm simplifying things, there's another class of exceptions called runtime exceptions, and there Java says you don't have to handle it, but you still often want to. Okay. So this is sort of like an act of God in construction, where it's not something. Actually, I don't think those are allowed in Canada. I think acts of God. But in the U.S., when you go look at construction contracts that we use to indemnify an old harmless dead company for acts of God, or something like that. And that means it's like so bad that we can't be accountable for it. It's just, it's a giant flood, which you couldn't anticipate, or earthquake would be more classic. So, ladies and gentlemen, exceptions. The language forces you to handle it. It forces you to do something about them. Bad things, rare things. Why rare? Why not use it for everything? This sounds great. It forces somebody to handle them. Why isn't that good? The memory overhead, they're slow. And this can be like night and day, folks. If you're throwing exceptions, you know, thousands of times a second, that sounds weird, but it can happen. You know, things like, oh, the network connection is lost, the network connection is lost, it's still lost, you know, just sitting there sort of freaking out. You think programmers still do that? Oh man, folks gotta get an imagination. It's fun. I talk with our IT people, with our tech staff in our department, and they think of it the same way. You know, I was talking to them, why is this computer so slow? They said, oh, it's probably freaking out. It's getting an interrupt from the disk drive saying, I don't know what to do, don't know. You know, that's why it's so slow. It's just sort of freaking out and screaming. And so they think of it kind of the same way I do. It's good to have imagination in computer science to appreciate what's going on. So with exceptions, they're expensive. I mean, I told you last time with exceptions, you know, if foo calls bar, and bar calls what? Baz, and Baz calls Zap, right? If you've got this kind of calling going on, and normally it returns a value back using the same sort of way, but otherwise it can throw an exception. It's got to actually remember sort of who along here handles the exception. So roll back the stack. It's actually got to keep a lot of other information around to do this job. So the gentleman back there has done right. It costs memory and it has performance issues. It's got to roll back the stack. It's got to knock all these things off. Maybe foo handles this. And when Zap throws it, it's got to erase that, it's got to erase that, it's got to erase that, and then the call goes again, and it erases, and it's just a lot going on. And it takes a lot of memory allocation and so on to do this. Create these objects that pass back as an exception object that are that big. So there's a lot of work. Return codes, when are they used? It's so common. It's going to be really common. And especially if it's not of such severity that it's necessarily a big problem. Use a return code. An example would be edit file. That's not necessarily a big problem that you reach the edit file. It's a fact of life. You're going to go through a file, you're going to reach the edit file. Okay, so certain files in Unix snap to the network, you might not reach the end. But most files you're going to reach the end. And you got to be able to handle it. And you want to handle it reasonably efficiently. So these are sort of common events. Particularly things, you know, if you're going to encounter them and they may be perfectly normal and not cause for alarm, a return code is good. But today, ladies and gentlemen, we're going to be talking about assertions. And we're going to have to dive into it because tempus fugit. Anyone know what that means? They're not teaching Latin in high schools anymore? Yeah. Time flies. Okay. So we're talking about assertions, and assertions are a type of offensive program. The idea here is, ladies and gentlemen, if you have a program and it has errors, you want to know about them as soon as possible. You want it to fail, you want it to fail hard. You want it to fail, when I say fail hard, I mean fail in a way that's obvious, so it alerts you. Now, ideally this is occurring during testing, or while it's on your desktop and you're doing unit testing on it, like you will for this one too. So here, we'll throw an assertion, and it may actually, often it just puts the program. It throws something up saying assertion failed on this line in this file, and you say, oh, now I know where to go look, and I go see, oh, this thing was past the low point. Okay, so that's good. Another type of offensive program, so when we talk about assertions, and assertions, ladies and gentlemen, are front and center. They're not just the bread and butter. I mean, they're an incredibly important part of quality assurance in real-life projects. Good code can be littered with assertions. Each function might be 10 lines, and 3 of them might be assertions, saying, this is true, or this assumption is true, this assumption. Basically, it's checking your assumptions, ladies and gentlemen. When you write this code with certain assumptions, and you learn as a habit to write those assumptions down, not just in comments, but in a statement called an assertion which checks them. So it's an operational way of specifying assertions. By operational, what I mean is that it's actually doing it. It specifies what your assumptions are, it's encoding them, but not really like a comment, which you might read or not. It's actually every time that function is running, it's checking. Is the thing passed to me non-null? Is the array passed to me have more than 0 elements in it? That makes sense? So if I'm going to be writing this code and I'm making some assumption, you just put it in an assertion. Now maybe that's part of my contract. Maybe my contract is say, hey, if I'm bar, you have to pass me a non-null pointer. That's great. But someone might say, pass me a null pointer anyway. Someone might make a mistake. They forget that their memory allocation can fail, and because of that, it gets a null pointer and passes it to you. And so you want to be able to check this thing. But this is one type of offensive programming. There's other types too. And in C, this is par for the course, folks. Ladies and gentlemen, I'd like to apologize for you for all those hours that you spent struggling with memory allocation in C. C is a tough neighborhood to be in. It's a great little language for learning some things, but it's got some rough members in the neighborhood. And pointers are kind of among the toughest. And part of the issue is you got to be. It's really powerful, but it's so powerful you can just cut off your arm with it. It's like a chainsaw. You can just cut your arm off like that. And you got to be really careful. You got to respect it. And you got to be meticulous and disciplined about how you do these things. So one of the things that we do to sort of guard against potential problems, we'll do something like we'll fill memory that's allocated. We do calc, allocate some memory, and then we fill it with illegal values. Why would we fill it with illegal values? That sounds perverse. Why do we fill it with bad stuff? Well, we fill it with those values until it's filled with good stuff. Okay? Or after we're done with having good stuff there, after we've freed it up, like just before deletion, we fill it with illegal data. Why would you do that? Well, because if somebody accidentally references it, they have a pointer to it, and they go and they grab something from it after the object's deleted. That's bad. It's bad. It's not allowed. They shouldn't be doing this. And we want to know if they're doing it, because we want to go fix that bug in the program. So filling it with illegal values, that might prevent someone from using a pointer to this to grab some data before it can be grabbed. So it would allow us to sort of recognize if someone's kind of going and using at an illegal time before it's ready. That's number 2. Or after its job in life has been done and it's gone, we're still sort of going and frogging it. That's number 3 of them. These are bad signs. Another thing is, so have you folks heard about the heap? Yeah, okay. So generally things live either on a stack, so food goes bar goes fast goes that. And this is growing on the stack, growing up. But then there's and that's some area of memory. Things live there. Variables live on the stack. They live out their life on the stack. I know these folks may think I live out my life on the stack. Maybe I do. It's a 2-level stack. another place that memory lives is in the heap. And where do we get things that live in the heap in C? We get them from, what do we do to get something in the heap? Yeah, we get these pointers, but pointers can actually point to the stack too. Oh man. I can give you some horror stories about that, okay? Bad things can happen when we point to the stack and then it freed up and we're still using that pointer. Bad things can happen. We can get our program to crash lickety split. But in the heap, folks, also we'll have a pointer to things in the heap. So there might be a pointer thing on the stack. Maybe we call it foo, call it var, and var call it fast. But we also might have another pointer that points to things in the heap. Where do we get? So this is automatically, when foo calls var, it's automatically put on the stack. The activation record, as we say, is put on the stack. The stack frame is another way to put it. It allocates space for all of the parameters of var when foo calls var. It allocates space for all of the local variables of var. Var declares inside of it an int. Maybe it's for total, let us the total up. That all goes on the stack. It all lives on the stack. Happily. At least I would have in the stack. But and so we can get a pointer to that. In fact, we pass around pointers to that sometimes with a banner. But we can also get a pointer to something else. Where else do pointers come from? We can get a pointer to point somewhere else. So where do we get that? I hope for assignment 2 you're going to remember this at least. Actually, you don't, because it's procedural C++. You're allowed to use new in that. Do you know new? Okay. You know new? So you can use new to get memory. You say new of this class, right? Or you can say new int, right? Create like a new array. Yeah. You can say new int, sort of like that, and it will create an array of it. Alternatively, folks, you could use calloc or malloc. This allocates stuff on the heap. And if we're allocating stuff, it turns out that sometimes pointers get pointed to the wrong thing in the heap. We increment the wrong. People said that was like P++, where you're incrementing a pointer. Yeah, you increment pointers, and you increment them sometimes too far. It's like you've told me about, go to this land in Saskatchewan. I go there, and then I start walking. Then I start walking out of that land, and I run into a gunfire range or something. And then bad things happen, okay? And it's like that with pointers sometimes. They get themselves into trouble, okay? So sometimes what we do is we can actually put certain things at the end of the heap. The heap has an end. It sounds weird. You know, sometimes people stop up at the mall because they want to hear what I'm saying. This is going to sound especially straight. But the heap has an end. It's not like the world which is round. It actually has an end to it on most systems. That is sort of the end of the memory the operating system is allocated. If you go beyond that, and the operating system is a bad thing, you're not allowed to be here, you're out of here. It's kind of like going to the U.S. border. If you try to go to the U.S. border and walk across it, they say, like, get out. Get over to the North Portal, or something like that. Or get over to the various places where you can cross. They'd stop you. So you can do that. And then if you put memory there, then if you go too far, then it will trigger an operating system problem. Alternatively, I talked last time about enums. You make the default value. C, for example, in your memory allocation may assign a value of 0 for things by default. You make that an illegal value. It doesn't stand for anything. And then you recognize, oh, if it's a 0, that means I haven't initialized it yet. I haven't put anything there, so I'll find it. So let's talk about assertions. So assertions are one technique in offensive programming. And their goal is to make the program that's buggy fail early. Fail early, fail often, so that you recognize where those bugs live, where you have a chance to go and find them. Why do we want to do that? Because we don't want the user to find the bugs, to be the first one to find the bugs. We want to be able to remove them from the program before the user gets them. So that's a big goal for it. But there's other benefits. So this reduces the likelihood that error will slip through. It forces us to buck up to the fact that we've got to fix this. Okay? Another benefit, though, is that it documents our assumptions. As I said before, it operationally encodes our assumptions. It describes our assumptions, sort of like a comment would, but in a more specific way, in a way that actually checks them. Actually checks them each time the code is wrong. Okay? And it reduces debugging time, helps us sort of find where the underlying fault is that led to a failure, and it helps improve the thoroughness of tests. So this is all, it sounds a little bit abstract. Let's go into some examples. So I want to show what they look like. So here's a case of some code we saw before. You folks remember this? This is the code originally called what? NR. Thank you. Good. Excellent. So this code was originally called NR, and we improved the variable names a bit. And here, the key point that I want to draw to your attention is it requires, as part of this definition of this code, it was something that turned up in testing, we were testing it, that it be passed the value for its first argument that's positive. Okay? It's a positive value. And so what do we do here? We assert that this value is positive. See that thing that says assert? Okay? That assert is basically going to test it. And if it's not positive, it's going to create an error message that indicates that an assertion has failed, but which assertion has failed and where it failed. Okay? So if you go and you look, and this is commonly in assert.h in C, what you see here is that pound defines this assert macro there, and that assert macro tests. Well, what is it doing? Like, who can tell me what that assert macro is? What is it doing? So that assert macro is turning into that code there. I was hoping I could find the laser pointer as feeble as it is, but alas, it eludes me. Oh, there we go. Okay. So what is this assert macro doing? This code, if I see an assert of some code, it turns into this code. What is this F? Yeah, so for our case, remember, these macros, they textually expand. So our F is what? It's actually this expression, n greater than 0. So when this thing gets expanded, F here is n greater than 0. It's not text, okay? And it gets expanded into this code. It'll be if what?
If that's true, nothing happens, otherwise you
Okay. And well spoken. What is that, if that is true? If n is greater than 0. So it's actually just going to blithely substitute n greater than 0. If it's true, do nothing. Otherwise, now what's this thing with this underbar file? Underbar. Does anyone know what these are? These things are predefined as part of the C preprocessor. When you compile your C code, it knows about these sort of things, and it will actually substitute something else for where this appears. So this underbar file, underbar. What does that actually get substituted in instead of that? The name of the C file you currently compile. How about line? Guess what that is? The line of code. So, ladies and gentlemen, what happens here is that we have, when we say this, assert n greater than 0, it turns into this if statement. You could just imagine it getting plucked down into this, just like that. It gets plucked down into this. It's testing if n greater than 0. If so, do nothing. Otherwise, call this assert routine with whatever the name of this file is. It might be Newton-Raphson.c, and then the line number of this place. Okay. Now, we call this thing, and what does this code do? Yeah. So basically, I mean, I don't want to go into all details here, but essentially what it's doing is it's printing out here the information on what failed. It says, which assertion, what will this thing be? This $S, what type of thing is that expecting? It's expecting a string, and what will that string be? The file name. This U line will be the line number. So ladies and gentlemen, this thing is turning into something where it's going to test if n is greater than 0. If it is, things are hunky-dory. And it just continues on. If it's not okay, it's going to print out this message, and actually normally what it does is it then aborts in a way that will cause sort of something visibly to come up to the user, okay? Now, when you have assertions defined in this way, we can use them in our testing. And in fact, in your assignment 2, you're going to be doing exactly that. You're going to be writing tests like this. So if this test passes, what's going to happen? This first one here. If it passes, what's going to happen then? Well, then it just goes on to the second one. If this test passes, goes on to the third. If it doesn't pass, what's going to happen? It's going to stop and fail, and good. Yeah, it's going to print out where it failed, right? It's going to print out that it failed at this place, namely the file and the line number. So we'll know which of these tests failed, okay? So that's sort of the basic mechanism of an assertion. I'd like to talk sort of on some of the things that we might check. And so in your assignment, I'm asking you to actually specify 3 things that you expect. You're writing the routine to divide the vector by a number. You might have some assumptions. You require certain things to be true, and so you're going to assert that. It's a precondition for unity to work. You need some things to be true. Maybe the vector is non-null, and so you're going to have an assertion that the vector is non-null. Postcondition. So your code supposedly does something. Maybe your code computes the square root of a number, and you can actually assert that the number you're returning is, in fact, if you square it, it's very close to the number that you were given as your argument. So if you're given an argument x, and you're returning some double precision value, you want to make sure, call it d, then you want to make sure that d times d lies within a very close level of x. Does that make sense? Okay, that's a postcondition. Sometimes you can test things really quickly. Among other things, you might want to make sure that d is also not negative, right? You're not returning a negative value, for example. It's going to be checking often things that are subject to logical oversights, or maybe a property of the data structure. The fact that all elements of this vector have to be negative or something like that. Or it may have to do with the internal consistency of the algorithm. Now, ladies and gentlemen, as you go on in computer science, you'll find that you're going to go on to take classes, for example, where you're figuring out clever, efficient ways to do something. So maybe it's sorting a bunch of numbers. You can do that inefficiently, you can do it efficiently. Both give you the same result, but one is much faster than the other. We talked about that at one point. But sometimes the one that does it really cleverly, that does it quickly, is actually more subtle. It's harder to get your mind around. And if you want to build confidence that it's working correctly, you can assert that the efficient one in a brute force algorithm is totally straightforward but inefficient, that they get the same results. Now, you may ask, why would you do that? I mean, why not just call the brute force algorithm? You're going to be spending all that time to do the brute force solution. You're going to do a bubble sort and a quick sort. Why don't you just do the bubble sort? That's going to take longer. Why do both? Well, the answer is, ladies and gentlemen, this test might only occur while we're running our code. So while we're testing our code, while we're running our code in the test labs, or while you're running it over in space, it's checking to make sure that it's consistent. And then when we give it to the user, that's stripped out. Then it's only used as a quick value. But this will be used during testing to reveal any subtle oversights when creating that efficient output. Another thing you might check is the heap corrupt. Oh man, heap corruption. Talk about bane of my existence. Corrupt heaps are no fun. It's like being told you have termites in your house or something like that. It's not a very good analogy. But a corrupt heap is bad news. It means that somewhere it's writing into a place that it shouldn't be, and tracking that down is often very difficult. So one thing you can do is litter your code with assertions that the heap is not up, and you'll be more likely to find it quickly after it happens to allow you to sort of track it down. Another thing is you check if a reference pass is null, for example. Here, you have refactoring of code. You take code that was ugly, and you're going to improve it, and we'll be seeing some of that likely in assignment 3. You have crufty code, and you're going to improve the quality of that code. Well, look, you have both code bases assert that the old code gives the same results as the new code until you're ready to jettison that old code file. Purge it from the system. Expurgate it. That was the first thing in the 50s. Using that word. Okay, so for example, you might say, hey, there's no duplicate entries in this array or something like that. Now, often these are stripped out at the time the code is given to the user. They're in there during debugging and testing, but they're stripped out when the code's finally delivered to the user. Because of that, some code out there, professional written code, will also attempt to handle these problems, even if they're asserted right now, so the program will just fail. Once the code is given to the user, we have some sort of error handling. Nothing you can do is tie it into logging, printing out what's going on, so it reports all these things. And you folks should make a habit, and I don't mean a habit for assignment 2. I don't mean, ladies and gentlemen, a habit merely for this course. I mean a habit for your life. When you're writing code, just reflexively, if you think about what am I assuming, write it down in assertion. It's really simple, it's really straightforward, and it will prevent you from getting into trouble. If you do get into trouble, it will tell you as soon as possible. Okay? What you cannot do is use assertions to handle unusual, quite possible situations. You do not, ladies and gentlemen, want to use an assertion to handle an out-of-memory error, or where the disk is full, because that is not due to a logical oversight. That is not something you can simply say must not happen. It is something which can happen, and you have to deal with maturely. It's not under your control. Assertions are used to check things that involve programmer oversights, misunderstandings, bugs, those sort of things, not for sort of inconvenient situations. So let's talk about some assertions. I do want to emphasize one thing. As a best practice, do not use side effects of assertions. Do not use the side effect of an assertion. Do not, within an assert, have actually a side effect. Why is that? There's actually 2 reasons I've shown you. One more obvious, one more subtle. Exactly. When the assert is gone, say in user code, when it's stripped out either directly or more commonly it's stripped out automatically, in other words, the compiler just ignores this if you tell it to. And that's part of the deal with assertions. You can tell the compiler, don't enable the assertions in this program. They're all still there in the code, it just ignores them. You can do that as part of the Java compiler's semantics, for example. You tell it, do not enable assertions, in which case this won't actually, it may appear in the source code, but it won't actually be in the code, be like a comment. It's on code. And therefore your side effect won't happen in that code. Could that be bad? yeah, if you tested your code on where the assertions are enabled, then you give the user code where certain side effects have been disabled, then you're not testing the user code. You're testing something that's different than the user code. So you don't want side effects in here because these assertions probably won't be there when you give the user your code. So that's one reason. A second reason, ladies and gentlemen, has to do with the general principle. Ooh, I guess it's a bit further on here. The general principle that when you expand this thing in a macro, you shouldn't have side effects when you call macros, because among other things, maybe here this only appears once, but maybe in general it could appear more than one time, and maybe it has a printf right here instead of down here, and in that case it's going to actually potentially do the side effect twice. Okay. Incidentally, this assertion here very commonly will further print out beyond the line number and the file number to actually print out what the assertion was, like n greater than 0 failed. Okay? Okay, so let's take a look at some assertions here. Okay, so here's a routine whose job in life it is to normalize an array. It takes an array and a length of that array, and it returns back an array that's like the original array, except it's been each element of the original array has been divided by the sum of all elements of that array. So imagine you had an array which had, 3 elements in it. Maybe it's 2 and 4 and 4. What's this going to return back? Maybe it's 2.0, 4.0, and 4.0. What's it going to return back? Well, it's going to return back 0.2. Why? It's 2 divided by 2 plus 4 plus 4. 10. And then 0.4 and 0.4. Okay? That's the normalized version of this array. That's what the job is. So precondition. Okay, so the preconditions is array is either null or it's got elements such that they sum up to something greater than 0. In other words, the sum of them is greater than 0. And what does it return? If those preconditions are met, what does it return? Well, if array is not null, if array is null, it returns null. Otherwise, if it's not null, it returns an array, where each element of that array returns is equal to the corresponding element of the array it got, this array it got in, divided by the sum of all the elements of that array. And what does it modify? What does it change? Like global variables, it doesn't change anything. It just returns this data. Okay? Okay, that's great. What can we check here as far as assertions? Well, one thing we can check is that if the array is null, well, first of all, if the array is null, we return null. If the array is not null, then we know the kind of elements has to be greater than or equal to 0. That's one of the arguments here. People can't say, oh, you have minus 3 elements in my array. We're going to assert that the minimum element of the array is greater than or equal to 0, which is one of the constraints here. And we're going to assert that the sum of the array is strictly greater than 0. Okay. Those would be things which we're assuming to do our work. We're dividing by the sum of the array, so we can simply say this array has a greater than sum. And you notice it does insert in the precondition that the array sums to greater than 0. Okay. And it also, yeah. Okay, so here's an additional C example. So here's identify index. So here we have an array, again, and we have a length of an array, count of elements. I forgot the second argument there. Hey, so this is int to match or something like that, value to match. So it takes in an array, it takes in a count of elements, and it takes in a value for which to search, and it's going to search through the array. What are the preconditions here? Well, I require, in this case, the array to be non-null. I'm just saying, I'm not going to handle null arrays. That's your job. Don't pass me a null array. So I can check that that's not null, And I can check that the count of elements, sorry folks, this should be greater than or equal to. I don't want someone passing me saying something. I've got a negative value number of elements in my bracket. Okay? So, do people see how these assertions are being used here? I'm making assumptions here. One of my assumptions here is that the thing has to be a non-null. That's specified in my specifications above. In my contract, I'm saying you can only give me non-null arrays. So, when I'm writing this code, I can assume that legitimately. I've just said it's a precondition for using me. You have to specify these things. And so I can therefore assert it. So when I run this code, what is this assert going to do? Yeah. It's going to check it, and if it ain't, it's going to throw an error message which says, you know, at this point in the code, this file, this line number, and in many assertion systems, this particular check failed. Go fix it. And naturally, that request is best passed to the program. That's the user. Similarly, this array here is going to be checking, is the thing passed to this effect? These things, ladies and gentlemen, are checking preconditions. But you could, further down in the code, have things which check post-conditions. For example, check that the value returned satisfies some properties, some general properties of the method, to make sure that the code's actually working properly. Okay, here's yet another example. Here, this example takes two arrays in each of their lengths, len 1 and len 2, and it returns the index of those arrays, the first index where those arrays differ from each other. Okay? So the first index, so it's matching up, you got A in this array, or it's an int array, those are int arrays, so you've got 1 is the first element of the first array, 1 is the first element of the second array, good enough. 2 is the second element of the first array, 2 is the second element of the second array, that's great. 3 is the first element of the first array, but we got 4, or minus 3, or whatever, is the third element of the second array, bad news. Okay, so it's going to, not bad news, just, that's the first index, 3, where they differ, so it's going to return 3. So this too has some preconditions. And we again encode these preconditions. And here we say, okay, either both of these arrays are null, or they're equal length. They can both be null, that's fine. In which case, we will return -1. If they actually do have elements, they got to be at the same length. Okay. And so either they're both null, or the lengths are equal for them. Those are preconditions for me to do my work, and someone else is responsible for them, so I'm going to assert them here. So in Java, we can have a similar thing, but we'd use what's called the assert statement. Ladies and gentlemen, this is a special statement in the language. Assertions are so fundamental to good programming, so central to modern software engineering, that Java as a language builds in an assertion statement. This assertion statement says, assert this condition, and then you've got a colon, and then you've got this message. And the message is from if the condition is false, if it's unable to succeed in that condition. So it'll throw this message if it's false. The beautiful thing is that we can enable assertions or disable assertions from Java compiler. So we could say compile our code and enable these assertions. These assertions will all be checked. Then later, maybe we're about to give the code to the user, we say disable the assertions. We have that code, we can give it to the user, and we know that even if the assertions would take up a lot of performance, we're imposing a lot of performance overhead. In other words, we're checking a lot of things that were very expensive, like running extra algorithms. Now they're disabled. We don't have to go and manually strip them out of the code. We don't have to go and comment them out. We instead just disable them this way. Does that make sense to people? Are people comfortable with that idea? So these assertions are things that check assumptions. I was going to cover this extra example. I'll let you muse on it from the slides. But this is an example, Java, from the Java programming language, which shows an example for assertions without an actual special method. Here we are checking a property of the thing that we're returning that it's got a null next element. Okay, I can explain this ahead of time. This is another time where we're replacing one value by another value in an array, and it's assuming that the value must always be present in the array, and if it's not, it'll actually complain about it. Okay, this is the final question I want to ask you folks. What's wrong with this? So based on all we've heard, based on what we've heard last time, based on what we've heard, ladies and gentlemen, this time, keeping in broader mind the bigger picture of exceptions and return codes and assertions and the issue of needing to be robust and handle problems, what's wrong with this code? Okay, so this code, its job in life is to duplicate a string. Takes a string in and returns a string, right? It's allocated to duplicate a string, it's returning that string. Okay? So here, we're going to first insist, it really should be up there in the specification, that the thing passed to us is not null. Someone can't be expected to duplicate a null string, in other words. We could say that, just like a contractor could say, hey, you're the one who wants to handle specified. Okay? So here, we really, if we're going to assert this, that's fine, but we should really put it up there as precondition. If someone's going to call us, they've got to pass us a non-null thing. Okay. So that's part of the contract. Okay, so this actual assertion is fine. How about this later assertion? Will it always go? Under what conditions will this fail? What does malloc do? It allocates memory, right? No? It allocates memory. So, does malloc always return null? Under what conditions will malloc return null? If you're out of memory. So for the most part, this code will run just fine. But when malloc returns null, this will fail, actually. In other words, when you're out of memory, this will fail. Ladies and gentlemen, should we be using an assertion when we're out of memory? No. An assertion is about checking our assumptions, particularly with respect to things like preconditions or assumptions, that we've actually done an algorithm correctly. It's basically about doing a sanity check that we as a programmer are doing things properly, that the code is correctly adhering to what's supposed to be guaranteed. Ladies and gentlemen, we as programmers have no jurisdiction over, we have no right to assume that someone who's using our program has arbitrary amounts of memory. We have to be able to handle memory of being out of memory.
That's exception.
Sorry, that's exception. It should throw an exception here, or if the language doesn't support exceptions, it could return a null value and just say, you know, if memory is exhausted, you have to handle it. Whoever called me has to handle it. But we cannot simply end the program and say, buddy, if you don't have enough memory, you're out of luck. We'll just bomb out of here. We should try to do something more. Among other things, ladies and gentlemen, you may ask, well, what can we do? It's hopeless. It's hopeless. Let's just give up. Well, it turns out, no. There's some basic things you can do. You can close files. If you have a file open, you can close it. If you have a database connection open, you can close that. You could print something to users so they know what went wrong. Maybe you can go free up some memory. Maybe they're taking tons of memory because they have the help system open, something like that. Maybe they're taking tons of memory because of one file they've opened, and you could You could say, okay, sorry, we had to close that file. There are things you can do with your out of memory. And one of them, at least you can clean up. So you don't leave things half corrupted in the file. Or you restore the original file over the file you were writing, something like that. So ladies and gentlemen, using assertions should not be used to handle inconvenient things. They are used to handle cases where our assumptions about that we've correctly built a program are in violation, or we've violated our rules for how that program should be used. We've made some logical oversight. This is not a logical oversight. This is a fact of life that memory can run out. Logical oversights are the province of assertions, not inconvenient things that we just don't want to handle. Okay? So, watch which things use exceptions for, return values, and assertions. Do remember that you've got to watch out for those inconvenient things. And I have to say, if it was a choice between doing this and doing nothing at all, I'd probably do this. Nothing at all, but this is not the proper province of assertions, it's a province of exceptions. Okay? That's all for today. Thanks. Thank you.